Chapter 14, Kinetics, Exercise 14.75. A reaction has a rate constant of 0.0122 per second at 400 Kelvin, 0.685 per second at 450 Kelvin. Based on the unit, you know it's first order reaction. And then we have the rate constant at different temperatures, and then we can use the Arrhenius equation to determine the activation barrier or activation energy for the reaction. The equation is this: Ln is equal to Ln minus E sub A over RT. This is the equation. But then we have two data points, so we can have K1 and then EA divided by RT1. That's my first equation, and I can have a second equation with Ln K2 is equal to Ln minus EA RT2. So we have these two equations right on the screen, and what I will do is I will use equation 2 minus equation 1. Well, you can do equation 1 minus equation 2 either way. What I will do is I will use this side minus, so over here Ln K2, the left hand side, minus the left hand side of equation 1. Alright, we have this, and then we have this part minus this part. Alright, and it's better to use parentheses, I believe, to make things more clear. Alright, that's it. We have two data points, and then Ln K2 is equal to this, Ln K1 is equal to this. So I'm gonna take the difference between Ln K2 and Ln K1. It's gonna be this expression minus this expression, and you can probably see Ln A and Ln A cancel. That's why we take the difference between two equations. Alright, and another thing is we have negative sign here, and it's going to be negative EA over R as the common factor. So what I will do is I will just get the common factor here. Alright, negative EA over R would be the common factor, and then multiplied by what? 1 over T2. So this is going to be just 1 over T2 minus 1 over T1. Sorry about this. I somehow cannot format this properly. Alright, okay, here's the equation we're going to use. We do have K1 and K2, we have T1 and T2, we just need to plug in numbers. Before we do that, Ln K2 minus Ln K1 is actually Ln K2 divided by K1. So I'm gonna do this. I'm not familiar with the format of this online calculator. Now we plug in numbers. Let's say this is K2, 0.685, K1 0.0122, R joule per mole Kelvin is the units of this value. 1 over T2, which is 400 Kelvin. Make sure you use Kelvin. And T1, this would be data point number 1 at 400. Oh, this is 400, and this one is 450. Alright, so this is the equation we need to solve. How do we solve this equation? It's pretty simple. I think both sides multiply by this number. Alright, and you'll get E sub A here, and both sides divided by -1 or multiplied by -1, it doesn't matter. Alright, I'm gonna say multiply by -1. We have this equation, and E sub A is the left hand side divided by the difference here. Alright, so what I'm gonna do is I'm gonna include everything on the left hand side into a pair of square parentheses and then divided by divided by this part. Alright, that's it. Over here, unfortunately, I don't think the square parenthesis is accepted. Now we have 120.6 or 121 kilojoule per mole. You can also use AXL to do this, but when you take an exam, you don't have a computer or Excel, so this is how you do this with a calculator. So this is how you do this with a calculator. Look at this equation. This equation comes from the Arrhenius equation. We just use the same Arrhenius equation for two data points. At temperature 1 you have K1, at temperature 2 you have K2, and then you take the difference and then you solve the equation. What's the value of the rate constant at 425 Kelvin? Alright, how do we tackle this problem, 425? It's pretty simple. As long as we have the value of E sub A, we should be able to get the value of A, and then we should be able to get the value of K at just any temperature. It's just that let's see, so this is E sub A. I just want to remind you, this is E sub A, right? E sub A is this. I'm going to use another trick to deal with this problem without even calculating the pre-exponential factor A. Of course, you can calculate the pre-exponential factor A and then determine the rate constant at any temperature, including 425. But because I have this value, 121 kilojoule per mole, so I know it's 121 kilojoule per mole. I'm converting this to joule per mole because this constant, this R constant, is in joule per mole Kelvin. So I just want to make sure that everything matches up. And now what I will do is this, 425 Kelvin, right? So I'm gonna change this temperature to 425, and this becomes the unknown. Now I'm gonna have to solve the value for K, and then that's it. That will be the rate constant at 425 Kelvin. And before we do any calculation, we know that temperature 425 is between these two, so the value of K should be between 0.0122 and 0.685. It should be in between. If you ask me to estimate, I think it's probably going to be 0.09-ish. That's my guess. In between, I'm just taking the geometric mean of the two values here because the temperature is the average of this two. So roughly, the rate constant at 425 K should be roughly 0.09. I don't know. We'll see. So we'll just solve this equation, right? We'll just solve this equation. This is how we get activation energy given two data points, and this is from part A. We solved the activation energy, which is 121,000. So based on this information, we just need to do this, and we just need to do this, and then divide it by negative R. That's going to be this part. Alright, and maybe we should do exponential, so to get this K over 0.0122. So let's see if we can do exponential here. I just copied this whole thing and delete, and then e to the power of that whole thing. Alright, very good. And this right hand side would be this, and finally K is just 0.0122 times this exponential term. All right, and we'll get this K at 425 Kelvin. It's actually 0.104. My estimate was 0.09, but I mean it's not too bad. It's not too bad. 3 figures. All right, so correct. Yeah, over here they also used the value of activation energy to compute the rate constant at a different temperature. But again, given the information we have, we can calculate the pre-exponential factor A. And then you simply use the Arrhenius equation to make predictions. You have A, the pre-exponential factor, and you have E sub A, the activation energy, and you can just easily get the value of the rate constant at any temperature. We do this only because we don't want to compute A.